Okay, this is the 15.8 video. I have some very sad news for you first, so you might want to grab a tissue. If you want to pause the video, get a tissue, prepare for my sad news. Okay, here it is. This is your last Calci video. I know, try not to cry. It's very sad. I'm so sorry. I wish there were more, but this is it. This is the last one. So, let's enjoy it. This is the divergence theorem. And we talked about divergence before. I don't remember what section, but we talked about it before. But this is here. Oh, there we go, for Green's theorem. So it would have been, I think that was 15.4. So anyway, this is kind of talking about what we've already done and kind of what we're doing now. So I'm not going to read it to you, but this is page 900. And you can read this little paragraph on your own. We're going to look at the formulas, though. So divergence, we have a vector field. M is in the I, N is in the J, P is in the K. And so the divergence, div for divergence, of F, the vector field, is the gradient vector dotted into the F. That's more, though, like a definition kind of formula. It's not the computational one that you're going to use. The computational one that you're going to use is this one. So for computational purposes, the divergence of F are all of these partial derivatives. So the partial of m with respect to x, partial of n with respect to y, partial of p with respect to z. Excuse me, sorry. And then here above example 1 is the physical interpretation of divergence in 3 dimensions. The divergence we did before was in 2 dimensions, and so this is now in 3 dimensions, but the applications are the same. Okay, so down here at the bottom of page 901, it talks about the divergence theorem and how it's related to the outward flux. That again we have seen before in 2 dimensions, but this is in 3 dimensions. So before it was with Green's theorem, you had for flux the double integral, and so now for divergence theorem we're going to have a triple integral. And again, this is not the form that you're going to use for computation purposes. I'll show it to you in a minute. The form that you're going to use for computation purposes, but you have here the outward flux. And then we're going to do now divergence with a triple integral. So I'm going to show it to you in my notes because I think it's a little bit easier to see. So here again is the divergence. This is the one that you use for computations. And then here, this one, this is not in your book. This is the one they have in your book. This is not in your book, but it's taking the gradient dotted into the F from up here and replacing it with this. And so that's where you get this from. So this is the one that you're actually going to use for computation. So the S that you see over here is the surface. D is the region enclosed by that surface, but down here D is actually a 3-dimensional solid. So you've got the surface S is kind of like the wrapping paper around it, and then the D is like the present inside. So it would be the solid part inside. Okay, and then again the one to the right is the one that you use for computation. So that's our formula. This is a very short section. There's not anything in here that we're going to do other than divergence theorem. So again, the D's here that we're going to be looking at are going to be 3-dimensional solids. Okay, let's turn the pages. So page 909, the first group of problems 1 through 4, it says find the divergence of the field. So these are vector fields, and we're trying to find the divergence of it. So for number 2, it's referring us to figure 1511. That's on page 836. So if you flip back over to page 836, here it is. That's figure 1511. So it's not actually the picture that you're looking at. It's this vector field. So this vector field is what you're using. So that's what we're going to use for this problem. So here was that vector field. M is the thing in front of the I. N is the thing in front of the J. This is just a 2-dimensional one, obviously. So we find our partial derivatives. Derivative of M with respect to X. Derivative of N with respect to Y. And then the divergence would just be the sum of those. So you're using this formula up here. You're not integrating, you're just doing the divergence. And so you add those together, and so it would be 2. So you try by yourself number 4. Here's what page it's on. It's referring you to, it's the same page, figure 513 on the same page. So pause the video and try that by yourself. Okay, so here's the picture. And they're not calling it capital F here, they're calling it V. But it's the same principle. So that V there is the capital F. Notice it's 3-dimensional, but it only has a K component. So this is written in cylindrical coordinates. See the R? So it's in cylindrical coordinates, so you got to change it back to rectangular. So z equals a squared minus r squared. Replace the r squared with an x squared plus Whoops, I left off my squared. Would it surprise you to know that when I was a student, I lost a lot of points for stupid mistakes? I pretty much never got 100 because I pretty much always did something stupid like that. So, I know that surprises you. Anyway, that's supposed to be that. Distribute your negative and you get this. So this would be in rectangular. The A is just a number. Okay, so here's my R rewritten in rectangular. So notice because I only have the the K coordinate, that's the P. I don't have a M or N. And so the derivative, M would be 0. N would be 0. The derivatives of zeros are just 0. So I didn't even do them. I just did the partial of P with respect to Z. But notice that P doesn't have any Z's in it. So it would also be 0. So all 3 of your partial derivatives are 0. So when you add them up, 0 plus 0 plus 0, you get 0. So 0 divergence here. All right, so let's try using this to compute flux. So number 6, here's the directions up here. Use the divergence theorem to find the outward flux. So for outward flux, obviously there's more than one way to do it. We've already seen in Green's theorem for the two-dimensional case. Excuse me, I think that was two-dimensional case. Maybe it was three-dimensional case. I don't know, whatever. We've done it before. Now that I'm thinking about it, I can't remember what it was. All this stuff runs together after a while. But here we're going to use the divergence theorem to do the flux. So number 6, it's the same vector field, but then it's 3 different D's. Remember, D is the solid that we're going to be integrating over. So the first 2 are cubes, but they have different bounds. So for all of them, because the F stays the same, the M and the N and the P stay the same, and so the partial derivatives stay the same. So I went ahead and found that here because that's going to be the same for all 3 parts. So first the cube, if it's formed by the coordinate planes and then the planes x equals 1, y equals 1, z equals 1, it would look like this. And your bounds would be all constants. They're all constants if you have, rectangles or squares, or in this case, cubes. So here's the formula that I'm going to use for flux for all 3 of these. So I just have, again, 0 to 1 for all of my bounds. Here's my 3 partial derivatives. This is a very simple integral, so you're integrating first with respect to z, plugging in, then you're integrating with respect to y, plugging in, then you're integrating with respect to x, plugging in, and you get 3. So 3 would be the outward flux computed by using the divergence theorem. Okay, so try part B by yourself. Part B, same idea, but the cube has different bounds on it. So part B, cube with different bounds. All right, so I didn't draw. I tried. You can see from all the white out, I tried. The coordinate plane, it should be easy to draw. It starts in the center of the cube, not the coordinate plane, the origin. The origin starts in the center of the cube, and so the z-axis would come out from the middle of the top, y-axis would come out from the middle of the right, x-axis would come out from the middle of the front. Sounds like it would be easy to do. For whatever reason, I just never could get it to look right. So that's why I didn't put my x, y, and z axes on there. But the origin would be in the center of that cube, if you can draw it and make it look good. Okay, so here's your flux formula. Same as the one before, except on the bottom I have -1s instead of zeros. So integrate with respect to z. Be careful with your negatives. Oh, next page, hold on. All right, and then integrate with respect to y. I was looking at an x when I said that. Integrate with respect to y, be careful with your negatives. And then lastly, integrate with respect to x, but notice what happens. You get 0. So that one, same principle, but different result. All right, and so for part C, you have a cylindrical can. So you've got the solid cylinder. This one here, it opens around the z-axis, but then you're cutting it off on the bottom by the plane z equals 0, which is the xy plane, and on the top by the plane z equals 1. So it's going to look like this, okay, radius 2, height 1. And so here it just makes sense because it's a cylinder to change to cylindrical coordinates because it's going to be easier to work with it that way. If you don't change to cylindrical coordinates, then here you're going to have to solve this for y, and you're going to have y equals plus or minus the square root of 4 minus x squared, and that's just a pain. So it's easier to switch to cylindrical. So here's cylindrical coordinates, and my z's between the 2 planes, because it's a cylinder of radius 2, my r is between 0 and 2, no restriction on my theta, and then you have to change this to polar also. So in polar, you're replacing the x and the y with r cosine and r sine. Then don't forget, because you changed it to polar, you have this r. I like to put it in the front. The book puts it between the dz and the dr, but as long as you have it on there, it doesn't matter. So first you're integrating. I forgot to distribute it because I actually forgot it, and then I added it later. So you can go ahead and distribute it now. I went ahead and integrated with respect to z, just again because I forgot my z the first time. So integrating with respect to z, and then plugging in, and then now before you integrate with respect to r, you have to distribute this r, because when you're integrating with respect to z, the r is just a constant, and so it doesn't matter if it's just out front because it's just a constant, like a number. But if you're integrating with respect to r, now all of a sudden you have a product of r times r's, and you cannot integrate products, and so now it's not okay to have that on there. So you do have to distribute it before you integrate with respect to r. So I distributed it, then I integrated with respect to r. Then plug in, simplify, integrate with respect to theta, plug in, and simplify. So that's all. I need some chapstick. I have the greatest chapstick ever. If you ever need chapstick, Skittles, they have Skittles chapstick. It's in Skittles flavors. It's fantastic. I highly recommend it. I would get some Skittles chapstick. Tell your mom that's what you want for Christmas. Skittles chapstick. It's great. Not as great as Hello Kitty and Auburn, but very close. Okay, last one. Are you sad? Wait, this is our last problem. Should we take a minute and cry? Pause the video, take a minute, cry about it, come back. It'll be okay. Every little thing is going to be all right. It's a song. Isn't that a song? I don't know. My daughter and I say that to each other all the time, and it's true. It's going to be all right. Okay, so number 12, last one. Same set of directions. Now we have a sphere. So sphere centered at the origin, radius A. Here's my vector field. So here's the M, N, and P. And so you want to start with the partial derivatives. Oh, I haven't done that yet. There they are. Okay, partial derivatives. There we go. There is my sphere. Okay, so because it's a sphere, I'm going to change to spherical coordinates. Because if I don't change to spherical coordinates, you can still do it. But you'll have up here z equals plus or minus the square root of a squared minus y squared minus x squared, and then you'll have a similar thing for the y, and it's just a big pain. It's so much easier to change to spherical. So in spherical, if you take this thing that you're integrating, factor out the 3, it becomes this. X squared plus y squared plus z squared is rho squared. And then when you change to spherical, I did remember it this time, you have the extra piece that pops up. So in spherical, the extra piece is rho squared sine phi. This was your function. Because it's the whole sphere, the radius is, or the rho is between 0 and a, phi between 0 and pi, theta between 0 and 2 pi, because no restrictions on either one of those. All right, so multiply together to get rho to the 4th, integrate with respect to rho, plug in, simplify. A is just the number, so just treat it like a number. Okay, so now you're going to integrate with respect to phi, plug in, simplify. And then integrating with respect to theta, remember A again is just a number, so you just stick a theta on the end, and it would just be this, 12 pi a to the 5th over 5. So that's it. That's divergence theorem. Again, it's just another way to do flux. Because chapter 15 is confusing in that it's a lot of different ways to do the same thing, I'm going to give you a sheet on Monday that's kind of an overview to chapter 15 and different ways to do things and how these formulas are the same and all that kind of stuff. So I will have that for you on Monday for you to look at. But you will learn better if you try to make one yourself. So if you try to make one yourself between now and Monday, a little kind of formula sheet guide to chapter 15, then when I give you mine on Monday, you can, just kind of compare and check and see if you got everything right. But the process of doing it yourself is a much better learning process than reading one that I've already made. So that will be my recommendation for you for over the weekend, to do that before Monday. And then also you'll get more out of the review day on Monday if you've done that first. So, all right, that's it for this video. That's it for chapter 15. That's it for Cal C. That's the whole book. Take a moment and be so proud of yourself. Hold on, wait. Let me show you. Look what comes after chapter 15, the appendix. So if you have taken all of your calculuses at UAH, you have probably used the same book the whole time. And so notice, take a moment to congratulate yourself. You started in Calais in chapter 1, and you have done every single chapter. Oh, wait, there's chapter 16 and 17. Oh, that's online. Just kidding. I was about to be really sad. That's online. It's not in your book. So you've done the whole book. Don't look at that because that'll depress you. You've done the whole book, all the way through 15, this whole book. Are you so proud? Take a moment, congratulate yourself, be proud, and study hard for your final exam. If you have any questions, send me an email.